So Chance has already foreshadowed that this is a good one. This question is pretty good. All right, so the principal ingredient of a certain commercial antacids, Tums, Chews, whatever, is calcium carbonate. A student titrates an antacid tablet weighing 0.542 grams with hydrochloric acid, and then it gives the reaction. I have two questions. Number one, we've asked this before. Anytime carbonate decomposes, what does it produce? A metallic oxide and carbon dioxide. Okay? Number two, looking at this yellow reaction, it says it was mixed with hydrochloric acid. Why is there no Cl? It's an ion. But why is it an ion? It's soluble. But remember, there's something I taught you a long time ago. When you're dealing with acids and bases, this is important. You're going to see this in a few minutes as well, besides this question. When you're dealing with acids and bases, if it's strong, what did you write? The ion. Because for bases as well. If it's weak, what did you write? The whole thing. So keep that in mind as we go throughout some of the things we're going to talk about today after this problem. Yes. Yes. They all connect. It does. Because if you go back and look at your solubility rules, which is your strong basis? Yep. Sir. Sir. No. You write the hydrogen ion for acids, the hydroxide ion for the base. Okay? All right. So again, you've already told me, and Dustin, you said a metallic oxide. Well, here's your metal. The oxygen must have been what? A spectator. So it disappeared. Carbon dioxide, and you got water. Okay? So if 38.5 grams of 0.2 molar hydrochloric acid is required for the complete reaction, what is the percent of calcium carbonate in the antacid tablet? So here's the crazy part. My first question to you is, what is the question? The percent of calcium carbonate. So let's start there. Now I'm going to kind of do some things out of order, but I think it's important that we understand this. So I'm looking for the percent of CaCO3. Do you agree with that? Now, here's the deal. What is the percent? Part over whole. What is the whole thing? Because what am I looking for the percent of calcium carbonate in? In the tablet. Would you agree with that? So I'm looking for the tablet. So what was the whole tablet? So 0.542 grams. Does that make sense? Now, so in this question, I have two pieces of data, right? I had the mass of the tablet and the volume and the concentration of the acid. Now it should be really simple what we have to do. I've got to take my piece of data that's remaining that I haven't used and convert it from the acid to what? Of calcium carbonate. It just get really easy, didn't it? So I need to. James is so mad right now. Hang on, let me say it. I need to go from the volume and concentration of the acid to the mass of the calcium carbonate. Would that give me my missing piece in my percentage? Because what are we solving for? Do you agree we're solving for the part? Hang on, what's the part? Calcium carbonate. I'm trying to calculate the grams of that stuff. Well, what am I given to get to that? I've been given that stuff. Yes? No? Go ahead. Because that's the molar mass of this compound. That's not the mass of the calcium carbonate specifically. Not how much it weighs in this thing. Because think about it, you're thinking that that's 1 mole of calcium carbonate. There is a 99.999% chance that it's not 1 mole of calcium carbonate in that tablet. Yes, of the tablet. All right, so here's what we got to do. So the first thing that I'm going to need is I need 0.542 0.038. No, that's not right. Yeah, I forgot the extra zero. 0.0385 liters. I am multiplying the volume times the concentration to get my what? Moles. That's my number of moles. That's my moles of hydrochloric acid. All right. Anybody got that? 0.0077, is it 0? Okay. Moles. So I'm going to rewrite this. Give me a second. I'll get out of your way. So 0.00770 moles of HCl. Yes. Yes. I knew. All right. So now this turns into a really easy problem. I'm going from moles of hydrochloric acid to what? Grams of calcium carbonate. Okay? Okay? This is what I meant a minute ago. H plus is representative of hydrochloric acid. Where did the Cl go? What's that S word? Spectator. It's hanging out. I don't need it, but it's still there, right? Yes, sir. No, because it said the principal ingredient of a antacid tablet is calcium carbonate. It's not the whole thing. I want to know how much of that tablet is calcium carbonate. Now, when it says the principal ingredient, what that means is that's what is attacking the heartburn. Does that make sense? Okay. So, do you agree that every medicine you take is not 100% the medicine? It's got fillers, flavors, coloring, all that other stuff. Okay. All right. Thank you, sir. I knew it was 100 point something. Okay. So, what we did, you've done this step many, many, many times. Okay. My mole to mole ratio, where does it come from? Coefficients. What is top to bottom? 1/2. Now that molar mass is, Madison, exactly what you just said. Now I want to show you why you can't do what you just said. You told me, why didn't I just add up the mass and plug it in up there in that yellow stuff with the orange circle? Look at what it would have been. You're telling me that in that tablet there's 100 grams of calcium carbonate, but the whole thing weighs 0.5 grams? You see what I'm saying? That's why you can't do it that way. We've got to find how much calcium carbonate react. Okay? Has anybody got an answer for this? All right, I'm going to go ahead and plug it in up here. 0.385 grams. Okay? Well, now it just turns into a percentage problem. I have to ask this question just to make sure we're on the same page. When you plug that orange number and yellow number in your calculator, is that the final answer? What do you do to it? Multiply by 100 or move the decimal 2 places to the right. I just want to make sure that you don't write down a decimal number. Because is it possible to have a percent that is a decimal? Yeah, it is possible, but don't assume that that's the answer. So what did you say it was? Very good. Okay. So, most of this tablet is calcium carbonate, 71% calcium carbonate. To be honest with you, percentages are one of those weird things that they don't always have to follow significant figure rules. But if it makes it work out, then yes. So just as a trend, do it to 3 sig figs. That's stuff to throw you off. That's exactly right. Them telling you about tums and chews and titrations and all that other junk is just to mess with your head. Okay? I think this is a good problem. So the crazy part about it is, like, the reality of it is when you actually take one of these things, you're only getting 71% of that thing you're taking that's the medicine. In this case, okay? In this case, it's that. So again, everything you take isn't always 100% of the medicine that you need. It is. It's significantly high. Man. It's when you are titration is when you're trying to find the concentration of an unknown solution. Exactly. What was the question? I need the percentage of calcium carbonate. When you see that word percent, I would always write percent, and sometimes I even write part over whole to get it in my mind that I've got to get part over whole somehow, some way. You know that's where you got to start, or you know that's where you got to end. You got to figure out how to get there. All right. I think the rest of it, chance is pretty simple, right? Okay. So does that make sense? All right. I don't really necessarily want to spend time doing these because I think they're super simple, but just reading this, it says what volume of a 0.075 molar cobalt-2 sulfate is required to completely react with that volume and that concentration of sodium hydroxide. What are you going to do here? All right, it is 1 and 2. Why isn't it not A and B? Fantastic. Love that. It's only a base. Cobalt-2 sulfate's not an acid. You guys could rearrange and solve for that, right? We're not going to go to that. Yes, ma'am. You should have them memorized by now. But no. Okay? All right. This is the exact same type of problem. Calculate the volume of a 0.309 molar sodium hydroxide required to completely react with that acid. And then B is that acid. That's A and B. And what specific part would you be calculating for? VB, the volume of the base. VB. Again, do we need to run through this? I think it's pretty. That's a plug and chug equation. Okay. All right, and then the last one, a 25 milliliter sample of calcium hydroxide requires to titrate with 12.4 milliliters of 0.1 molar HCl in an acid-base titration. What is the molarity of CaOH2? Again, what are you doing? You've got two volumes and one molarity, and you're looking for a molarity. So what would you be using? This is AB. This is acid-base. Okay. What would you be solving for specifically? MB. Molarity of the base. Does that make sense? Nicole, are you with me at all? Okay. Jamil, you with me? What's the question? The molarity of CaOH. CaOH is the base, right? That's MB. So you'd solve for MB. You with me? Okay. And I think that is it. Alright, so let me pause this and we'll give you something else. Okay, so this is the first one I want to look at. It says, it's got two pictures here. It says the structure of a water molecule and a crystal of Ki are represented above. A. Explain how you would prepare a 1 milliliter solution of a 1.0 molar Ki solution. Include appropriate calculations in your response. My bad. 100 milliliters of a 1 molar solution of Ki. Now, I'm not going to spend a whole lot of time going over this one. The first thing that I want to mention to you is this making a solution or diluting a solution? Making a solution. So making means grams. And that's what it means by include appropriate calculations. So what would you have to do? Have to find the mass of Ki. Now, so how would we do that? We got a volume and a concentration. Multiply it to get the number of moles. Then when you get moles, you get grams. Okay. Once you get your grams, now again, we're not going to do the calculations. That you can do that on your own. The part that I want to verbally discuss is how would you then make your solution. And I need you to make sure you go back and reread all that stuff we talked about in the first part. Okay? Again, I'm going to say it out loud. I don't want to talk about it as far as what you do, how you do it. And again, you can change it, you can edit, you can add it, but this is a basic kind of minimum statement. You would mass out how many ever grams you need. Has anybody already got that? I know some of you are super nerds. Okay. How many ever it is. You mass it out in a weigh boat on a digital scale. Right? Okay. You pour the solid into how big of a what? You don't need it, guys. Don't get a calculator. Don't get one. You don't need one. No. We're just talking about it out loud. Okay. If you want to, that's fine, but I'm just talking about it out loud. Okay? You should know how to do this. The part A is not what I'm worried about. I'm worried about part B, which we're going to talk about in a second. So part A, you're going to mass out whatever the mass is on a weigh boat in a graduated, or in a weigh boat on a graduated cylinder. Excuse me, balance. You're going to pour in that solid into a 100 milliliter volumetric flask. Okay? You will then pour in enough warm distilled water to do what? To dissolve by swirling completely. Dissolve completely by swirling. Then you will fill the remainder of the flask up to where? The etching or the line or whatever on the neck of the flask. And then the most crucial and critical part is the very last sentence says you need to tell me what you just made. This would produce a what? 100 milliliters of a 1.0 molar Ki solution. That needs to be your final sentence. Does that make sense? Okay, we're good. So part A is all on your own. Yes, sir. No, that's the only. You only use that in the very first part. Okay. All right. B. In the space below, this is the reason we're looking at this sheet. In the space below, provided below, show the interaction of the components of Ki aqueous. As soon as it says aqueous, what does that tell you about this solid? It is in ion form. These are ions. By making a drawing that represents the different particles present in the solution. Base the particles in your drawing on the particles shown in the representations above. So here's the important part. Do you need to know what those things look like to incorporate them? Yes. Don't make it up. Do it as they have it. Include only one formula unit of Ki. In your homework, some of you have seen this question. Here's the crazy part, and this is something that I mentioned a long time ago and most of you don't remember. When you hear the word molecule, what does that represent? Covalent bond. This is something I never talked about. I mentioned it once and we went right through it. When you see the word formula unit, that means an ionic bond. Hold up, we're going to get there. So here's the deal. It says include only how many Ki's? One. So according to the chemical formula, you need how many K's and how many I's? One each, right? Now, just a minute ago, you told me that where it says Ki aqueous stands for what? Ions. Look at this picture. It's a Ki what? Which means you need to do what? Separate it into their ions. Does that answer your question? Okay? So, and then in the important part, this is the part where you got to read. And this is the part that scares me because you guys can read, you don't read. And no more than how many molecules of water? 10. No more than. Doesn't give you a minimum. At least do 3. At a minimum, do 3. That's around each one. That's a total of how many? 6. Are you below your maximum? Yes. Your drawing must include the following details. Identity of the ions, symbol, and charge. Let me finish. No more questions. Let me finish. Number 2, the arrangement and proper orientation of the particles in solution. So here's the deal. When I draw my Ki ions, look up there at your crystal. You have to use the picture as your reference in the drawing. Your Ki crystal has 2 different types of circles, correct or incorrect? Large and small. You have to have one that's large and one that's small. Your challenge is figuring out which one goes with which size. Which ion is which size? the anions are bigger. That's something you have to have in your concrete foundational skill of when you draw this stuff. So here's how I would do it. Again, how many KIs do you need? 1. So you need 1K, and then, is it I or CL? My bad. Significantly. Now, when we say significantly, it has to be visually different. So when you read the rubric, it would say something about there is an obvious or visual differentiation in size of the ions. Okay? Now, if you want to shade it, that's fine. So it's just like Trevor said. If you want to do one hollow and one larger, but here's the deal. If you draw that inside the box, Trevor, here's the problem that's going to happen. Did you prove to me that you know which one was which? So if you wanted to, underneath it or out beside it, a key, you could write K minus and I minus. That's fine. However you want to do it is fine. I'm just trying to, you can draw hollow and shade it, but you still need to prove that you know which one is which. Okay? Yes. No, just because the picture has it shaded. Does that make sense? And on the drawing that you guys have, you can't tell, but in this one you can tell. Does that make sense now? Okay. What? All right. Now, we need to draw water. So, and it says the proper orientations of the molecules. This is the part where the water comes into play. Is there a specific way that the water must be drawn around each ion? All right. So, it's going to kiss the positive. But I love it, though. It's great. You have to draw it like that because the instructions tell you to use the representations above as the drawing. No, and here's why. They assume that you know that water is represented like Mickey Mouse, and that the face is the oxygen and the two ears are the hydrogen. That is an assumption that at this point in your knowledge you already know that, so you don't have to label it. Don't worry about shading. You're too caught up in the shading. It just has to be the ions have to be different sizes, and the water molecules have to be facing the right way. That's the expectation. This is in fact, that would earn you full credit for that question. Okay? Yes, ma'am. That's it. You're done. You're finished. There's nothing left to do. Too many, Jamila, you had a question. I'll come back to you. You would write on the lines, and then you would draw this in that box. Okay? You would, I'm going to go ahead and tell you, on the real exam, it would say, use the space provided below, and what happens is the lines are below the question on the real exam, and you would just draw it in that box. So when they get your exam, like, your question, all your work, and all your answers are there, they'll just look in that box for your answer. The beaker you'll be given. Maybe. Depends. May not be in this exact form, but How hard is that? Most definitely explanation for sure. Yes, most definitely. I'm not going to be here tomorrow. That's Monday. She's going to be here, yes. Why do you have so many questions? Oh my gosh. I think so. Yes. 5 each. Yes. Okay? All right, so we're done with this. We're finished with that right there. All right, so here's what I want to do next. This is practicing net ionics. These are your net ionics, and I'm going to go ahead and tell you that these are going to be a little more challenging than you've seen because it's going a little bit more in depth. Let me just go ahead and tell you, prior to the redesign 3 years ago, this was question number 4 every year. Okay, I'm just going to, this is the whole packet. These were questions throughout all the years, and notice what they do. They look identical to each other, and they're all net ionics. This was question 4 every single year until they decided to change it a few years back, so it's no longer part of it. But you could guarantee this question every year, and it looked just like that. Okay, so we're going to go ahead. We're going to practice. We're going to practice through these. Okay, so and the reason why I'm showing you these is because I think it's important that you can do these net ionic, the complicated ones. So when you have the easy ones, you got them. Okay, so I'm going to do the left side with you. There's 2 different ones. If you read the questions, they're 2 different ones. They look identical. They're 2 different questions. I'm going to do the left side with you, and then I'm going to give you a chance to do the right side on your own. Sir? Yes. Okay. So A, it says dilute hydrochloric acid. And this is how I need you to read this if this were like a paragraph. When you see that, an alarm should be going off in your head. When you see the word acid or you see the word base or you recognize a base, you need to ask yourself one question. Is it strong or is it weak? Hydrochloric acid is an SA. It is a strong acid. Now, just a few minutes ago, I told you this. When you see a strong acid, what do you write? H plus. Yes. We're not finished yet. We're not finished yet. Okay. Then is added to a solution of. As soon as you see solution, you can write the word ions, which is right, that's aqueous. But then when you see ions and you see solution, you see aqueous, you need to think solubility rules. Is there anything in there that can go away? And what are we left with? What are you talking about? Yeah. You guys are thinking too much. Quit thinking. Stop thinking. Yes, because y'all talk way too much. Now, this is the problem, Dustin. Dustin, you just told me that what are we going to make? Am I? Carbonates decompose into carbon dioxide because the hydrochloric acid is breaking down that carbonate ion. That's the I'm teaching. Okay, I'm teaching. Here's the deal. Holy crap. Dustin, you're right in a sense that we're going to make carbonic acid. But there's a word that you guys are going to learn later called an intermediate. And this is the problem, is that carbonic acid is going to form for just a few seconds, a few minutes, maybe a few hours. But what is that carbonic acid eventually going to do? It's eventually going to break down. When you have Coca-Cola, what do Coca-Colas eventually do? They become flat. What is the acid in Coca-Cola? Carbonic acid. Now, I know that is a stretch for you to get to, and that's why I teach. This is why we stand up here and we talk about these things, is because your reality sometimes is time restricted. You don't think about the longevity of what happens over time. Coca-Cola doesn't stay pressurized forever. It eventually will leak and it will eventually break down. Okay? So just keep that in mind as we go through all of this stuff. Is that the only reason that this is the result and not carbonic acid is because will it always stay carbonic acid? No. What do all Coca-Colas eventually turn into? Sugar water, which is exactly what a flat Coke is, right? All the carbonation has bubbled itself out. Sir. Yes, there's no acid in it. It's sugar water. Yes. Well, think about it. Is a seal always perfect? No. Eventually that seal will, over a long period of time. Yes, ma'am. Okay, can we, I don't, this is the netonic. Thank you. Final question, number two. It says, describe a test to positively identify the gaseous product. And these were the fun questions to me. Some of them were really hard, but some of them were actually really fun to think about. First of all, my question is, what is the gaseous product? All right, so we know that this is going to be the gaseous product. So how can we identify a gaseous product? Okay, but how could I tell what it was? It's a gas. Thank you. Put a match to it. What does carbon dioxide do to flame? It snuffs it out. Okay? When you blow on a flame, what does it do? It blows it out. It's not the power of the wind. No! Holy crap. Holy crap. Yes, thank you. Yes, this wine goes out. So, this is what it says. Listen, this is what it says. You don't have to get this technical. It says a glowing splint, which is nothing more than a match or a piece of wood on fire, will be extinguished in the presence of carbon dioxide. So literally, if you put in a match, it will go out. Well, you're learning. No questions. No questions. No questions. B, water is added to a sample of solid magnesium nitride. Is there anything we can bust in this question? No. You don't bust solids, liquids, or gases. Does it tell you what water is? It doesn't matter. It's a solid, a liquid, or a gas. Leave it alone. Okay? So it's H2O plus. What does it tell you about magnesium nitride? In 10 seconds, without asking a question, write down the chemical formula of magnesium nitride. Don't ask a question. Shh. What, I? Oh, you have to read the instructions. Yeah, I think it actually says up there in part I, write the netonic. This is one of the ones that's going to get you two. Okay? Again, this is why we're going through these things, so you're not freaked out when you see them. A metal nitride. And again, this is one of the common the things that was on that sheet at the very beginning. A metal nitride, when mixed with water, will produce these two things. Not an oxide. Hydroxide. All right, so let's think. Let's look at what we've used. We've used our O and we used our Mg. So we've got an N and an H left. Very good. Very good. Ammonium. A metal nitride, when mixed with water, will make a metal hydroxide and ammonium. Now, why don't I keep saying the word metal? Can it be any metal and it do the same thing? Lithium, calcium, barium, any of those make the same thing. Ammonia. A metal nitride will react with water and make a metal hydroxide and ammonia. I could make this lithium nitride, and it's lithium hydroxide and ammonium. Yes. Sure. Okay. Describe any change in color or odor. I like what Dustin said. Could you check the pH of the solution? What would it be? It'd be basic. That's one. Okay. Is there a smell? Very good. Okay. So there's two things. You've got the pH equals more basic. Yeah, we'll go back and do that. And then the smell is ammonia. Okay. Let's see. I've got two H's, three H's. That's the problem. I'm going to give me a 3 here and a 2 here, and I think that balances it. Nope. I need to. Oh yeah, that's right. That's right. Thank you. All right. So I need 3. That gives me 3. That. Okay. Thank you. Yep. The reason it changes, and that's what we're saying. The color, if you put like an indicator in it, it'll change to a basic color. If you do a pH paper, it'll change the pH color, the pH paper. Because it produced a base. Gotcha. All right, no more questions. Okay. Yes. They would never ask you about a smell unless it's something that you know for a fact has an odor. Ammonia, we know has an odor. Never. Carb. I've never said that ever. A bleach. You can't mix bleach and ammonia cleaning products. Okay. All right. C. Real quick, before we do anything. Okay. C. Ethanol is burned in oxygen. Give everybody a chance. You guys write the reactants. Ethanol, burned, oxygen. Don't say anything out loud. No questions. Sorry, Dustin. You guys aren't used to having to remember so many details. That's why this class is not easy. All right, so since most of you are like, I don't know. Eth means what? 2. C, 2. Okay? We know that anol means OH. So it's got to be H something OH. Not in this case. All right, so here's my question. Every carbon has how many bond locations? 4. Do you agree that that takes up one of them? Okay, so 1, 2, 3, 4, 5, 6. We've got 6 left. But is it H6? No, because one of the other bonds is taken up by a what? It's taken up by an OH. So how many H's do you have? 5. Meth, eth, prop, and bute. Now, when it says burned in oxygen, I'm going to kick you in your shin if you write that letter right there. Thank you. Now, you should very much recognize this type of reaction. It is a combustion reaction. Wow. Wowzers. Wowzers. Now, this will take a little while to balance. I don't care. I want you to balance it. Don't give me an answer. I want you to balance it. Okay? Number 2. You balance it, but let's kind of skip it for just a second. Number 2, identify a possible source of activation energy for this reaction. Perfect. As a matter of fact, that's one of the words they give you. You can, well, let me read you what it says. A lit match, spark, or other ignition source could ignite this mixture. I would say fire, but enough heat to spark it. Enough heat. So you could say fire or spark. It says verbatim, a lit match, comma, spark, comma, or other ignition source to ignite it. Fire is a good answer. Sure. I wouldn't write that word, but sure. Perfect. All right. So that's the left side. Do you agree that these have been a little more challenging? So here's what I want you to do. I'm gonna pause the video. I want you guys to see if you can do the other side. Okay? All right. So, a piece of aluminum metal. So let's start there. What state of matter is that? Solid. So let's leave it. Okay? So I've got Al is added to a solution of. So as soon as you see solution, you can think ions of silver nitrate. Can I get rid of anything? Nitrate, very good. So I've got Ag+. Now, so really, this is what type of reaction? Single replacement. So aluminum is going to swap with silver, and aluminum is going to go from the metal to the what? To the ion. So Al what? 3+. And silver is going to go from the ion to the what? Solid. So Ag. Now this is when it gets a little weird. If you left it like that, did you get it right? What's wrong? The charges aren't balanced. And this is one of those weird situations where you got to really know that to catch it. So I've got Al, I've got one positive on the left, 3 positive on the right. So what do I need? All right, so I need a 3 here and a 3 over there. That is balanced. How many of you got that perfect? Very good chance. No. Wow. Okay. Now, this next question, again, is no longer going to be asked, but this is why I teach it the way I teach it. The question says, which substance is the reducing agent? So if you set these two things up in your ox and Ra and your red cat Oa, then you know. You know who the reducing agent is. It's the one that goes through what? Oxidation. Whose charge went up? Aluminum. So aluminum, because it says explain, because it did what? It oxidized. Okay? Because it oxidized. Okay? That one wasn't bad, was it? You know what the part that got everybody when they took it? Balancing. And it is. It's easy to miss that part. But those are the things as we progress we got to get better at. You would not get credit. The reason why is because these say, for each of the following three reactions, write the balanced equation. Really, you have to have the net ionic. I know it's understood to be net ionic. Okay, but again, these questions are no longer on the exam. All right, B, solid lithium hydride. So what do you write? LiH is added to water. So we're always going to write water. Again, this is one of those nuances that you just have to learn with experience over time. Metal hydrides produce what? Metal hydroxides and H2. This is the part that's going to make some of you really upset. And I know that this is where people get really mad and really frustrated with chemistry sometimes, but I can't do anything about it. I'm going to write the correct answer, and then I want you to tell me why it is written this way. Why? Bingo. Now, because it's a strong base, you must write it dissociated. And I know what you're thinking. If it's dissociated, lithium's a group 1, why is it still there? And that's the important part. Remember, we only cancel what changes, what stays the same. Did lithium change states of matter? It went from a solid to a what? An ion. That's the only reason it stayed. This is a tough question. Let me tell you how they graded these. They gave you 1 point for the correct reactants, 2 points for the correct products, 1 point for the correct balance. Most people got the 1 point for the reactants, right? There are very few people that got the 2 points for the products, but the balancing part is easy. Okay? The balance is easy. If you had written LiOH together, you would have gotten 2 points, not 4. Does that make sense? Okay, which is fair. 2 points is good. And then the 5th point came from the analytical question. If phenolphthalein indicator is added to the final solution, what is the color of the solution? Okay, let me tell you what they say. They say, ooh. Y'all are going to throw something at me. Dustin, do you know what it is? It is pink. No. Well, no, you're right. Keep going. With that indicator. No, phenolphthalein is colorless when it's an acid and pink when it's a base. I promise you, this is your lack of skill today. May 1st, that will be hammered into your skull. You'll know it. I promise. That's what they were doing with the titration. When the pink drop hit and it spun, it turned back clear. I didn't catch that it was a phenolphthalein. That's my fault. The pinker it gets. Yep. Okay. All right, last one. This is an easy one too. Chlorine gas is bubbled. So chlorine, what is that? Cl2 is bubbled into a solution. What do you know when you write when you see solution? Ions of potassium iodide. Can you get rid of anything? Very good. So we've got plus, I, minus. Now, this one's just like the first one. What type of reaction is this? Single replacement. But the tricky part about this one is we know chlorine's going to go from Cl2 to the ion, but what is I going to turn into? I2. Okay? But last question, is it balanced? Nope. And again, you would have gotten a point for doubling that and doubling that. Yep. Here's something that is another topic that you will not be tested on. Okay? I'm telling you, you don't have to know this. You used to, but not anymore. And that was the color of ions in solution. Okay? One of the old things you had to know is if they gave you this solution, what color would it be? That's old. You don't have to know that anymore. This is what it says. If the solution remains aqueous, the color is amber. What is amber? It's like a reddish, orangish, brown mix, right? Okay. It says the color is amber since iodine is the only slightly soluble. Think about that. When y'all go to the doctor and they rub that iodine on you, what color is it? It's that doo-doo brown looking color, right? Okay, that's what color it would be. I don't think doo-doo brown would be appropriate to write here. So they chose amber as their color. But when you hear the medical iodine, that's why it's brown. So another piece of knowledge that you knew that you didn't know why you knew it. It's an anesthetic, which means it's sterile, it's clean. It's a sterilizer. It's a little different. Okay. So if the solution remains aqueous, it's amber. If it's a solid, and I'm going to be 100% honest with you. If it's a solid, it will turn purple. That's another thing. Iodine. Now, we talked about this yesterday. What color is iodine on the periodic table? It's a solid. It's black. So if it's iodine is a solid, it's purple. It's purple. That's cool. I didn't know that. Okay. Okay, what? It turns into one, yes. They're giving you the option to say both. Okay. All right. Any more questions?